All right, everybody. Welcome back to the second instructional video for week 4. We're going to cover a new gas law called the ideal gas law in this video. We're going to talk about how we came up with the relationship, how we derive or calculate the ideal gas constant, which allows this gas law to work, and then walk through some calculations. At the end of the previous video, we saw that no matter what pressure, volume, molar amount, and temperature we had for any given gas, PV over NT always gave us a constant answer, gave us the same calculated value all the time. What I want to go through with you is how do we get this arrangement? So how did we come up with PV over NT? Because we just kind of jumped in and assumed that was a true statement. Well, if we look at the combined gas law that we already knew from last week, we saw that P and V are inverse, they're inline inverse with each other, but they're both directly proportional to temperature. We learned the same thing with pressure and volume. Both of those are directly proportional to molar amount. We talked about that in video 1 this week. Pressure goes up when the amount goes up. Volume goes up when the amount goes up. So PV over N is just as true as PV over T. Well, if we take both of these equations and we superimpose them on top of each other, we get this equation in the middle. We get pressure and volume are inverse to each other, but they are both directly proportional to amount and temperature. So we end up with this PV over NT. We get this central equation here when we put all of that information together. So we got PV over NT by taking the combined gas law and what we learned about pressure, volume, and amount in the last video, and just smashing that all together in one equation. Now, the tricky part is, with this point, we would have an equation with 8 variables. So imagine having to list out in your problem P1, P2, V1, V2, N1, N2, T1, T2. That seems like a really huge pain in the butt. There's a way to simplify this, though. What if we always compared the sample of gas we're dealing with and the conditions that it's at? What if we always compared it to standard conditions? 1 mole, 273 Kelvin, 1 atmosphere, 22.4 liters. If we always plugged the same values in for N2, T2, P2, and V2, well, then we would have a constant number on the right side. That's where we get this ideal gas constant. R is what we use to represent the ideal gas constant. The neat thing about this R, when we see R in our equation, it is a set of conditions. R is standard conditions. It is standard pressure and temperature and standard molar volume all put together. 1 mole at STP is 22.4 liters. The units will change depending on which pressure unit you use. Are you going to use atmospheres, millimeters of mercury, or kilopascals? Depending on which of those you use, your R number will change. But every time you use standard pressure and atmospheres, you're always going to get the same number for R. Let's take a look on the next slide here and we'll look at these. So you have 3 different standard constants. The first one that we're going to go over is the most common. You can always convert a pressure to atmospheres and then use this all the time. The calculation practice we're going to look at with Tyler DeWitt after this, he's going to talk about doing that. But to find the ideal gas constant, if our pressure in the problem is in ATM, we take PV over NT, standard pressure at 1 atmosphere, standard molar volume, 22.4 liters. Standard molar amount would be 1 mole and standard temperature is 273. If we take 1 times 22.4 divided by 1 divided by 273, we get 0.0821. The interesting thing is ATM, mole, liter, and Kelvin, they don't cancel out. So we have to keep all of those units. So we end up with this pretty large derived unit cluster over here. Standard conditions with pressure and atmospheres is 0.0821 ATM liters over mole K. If we plug in 760 millimeters of mercury instead of 1 atmosphere, so let's say the pressure was given to you in millimeters of mercury in the problem, then you could use 62.36 millimeters of mercury liters over mole K. How do we come up with this 62.36? How do we know this constant value? Take your standard pressure, your standard molar volume, standard molar amount, 1 mole, and standard temperature, you plug them all in. If we substitute in 101.325 kPa for standard pressure, and we use our standard molar volume, standard molar amount, and our standard temperature at 273 Kelvin, and we get 8.314 kPa liters over mole K. So these are the R values. You can write these down. You can print these off. Reference this when we get to the practice problems later in the week. It would be probably a good idea to have these 3 written down. If your pressure in the problem is in atmospheres, you would use this one. If the pressure in the problem is millimeters of mercury, use the second one. If they give you the pressure in kilopascal, then use the 8.314. Your pressure units have to match the units in the problem. Your volume always has to be in liters. Your temperature always has to be in Kelvin. Your amount always has to be in moles. Now, by calculating our R value, instead of writing out P1, V1, N1, T1 equals P2, V2 over N2, T2, we can take that whole right side of the equation and just write R and use that 0.0821 unit, 62.36, or the 8.314, depending on what pressure they gave us in the problem. And now we have PV over NT equals R. That's much simpler. Even simpler yet is what if we take everything and make it linear? In other words, get rid of the N1, T1 on the bottom and make it a linear equation, everything in the numerator. We get PV equals nRT, more commonly referred to as PivNert. Yes, PivNert. If you can remember PivNert, you know the ideal gas law equation, PV equals nRT. All right? Now, when do we use this gas law? Anytime you're given only one set of data. They ask you, what's the volume if you have 3 moles of gas at 4 atmospheres of pressure and 37 degrees Celsius, which would be 273 plus 37 is 310 Kelvin. If they give you a pressure, a temperature, and an amount, and they ask you for the volume, well, they only gave you one set of data. You can't use the combined gas law. What are the other pressure units you're going to use? What are the other volumes or temperatures? Anytime they give you one set of data, use the ideal gas law. If the pressure in the problem is not given to you in atmospheres, you have 2 options. We talked about one already. Pick a different R value. If it's given to you in kPa, then use the 8.314 kPa liters over mole K as your R value. If it's given to you in millimeters of mercury, then use the 62.36 millimeters of mercury over liters over mole K. Or you can just do a simple, quick conversion, realizing that we know these 3 pressures are all the same. 101.325 kPa is 1 atmosphere, is 760 millimeters of mercury. So if they gave you 825 millimeters of mercury, and you're like, man, I don't remember what R in millimeters of mercury is, but I know 0.0821 ATM liters over mole K. Well, then just multiply it by 1 ATM over 760 millimeters of mercury, and you'll get 1.09 atmospheres. Now you can use your R equals 0.0821 ATM liters over mole K. Now, I could walk you through a ton of practice problems at this point. I'm going to put down in the assignment, there'll be a link. Here's the link as well for some practice problems that Tyler DeWitt walks through. I'm also going to post some videos from other sources. I think Mr. Highland put out a video, so I'll probably post a link to his video up there as well. Biggest thing to remember, ideal gas law. We use it when there's one set of data. There isn't two pressures, two volumes, two amounts. Only one set of data is given. In order for this to work, you have to match all of your units to the R value. So R for atmospheres is ATM atmospheres, L liters. So your volume has to be in liters. If it's not there, convert it. Moles, make sure your amount is in moles. And then Kelvin, always for calculations, use Kelvin. I'm going to cut this off here and try to keep this one short. Check out the practice problems that Tyler DeWitt walks you through on this link. I'll put it in the link below as well. Stay healthy, be strong, improve daily. And as always, any questions, please put them in the Q&A or at the comments at the bottom of this lesson. Email me if you want a quick response. I can get back to you quickest if you email me at PTSD Web Apps.